move around the telescope by hand, bodily, and you try to minimize the shadow. And then we have this little thing called a soul searcher. It doesn't search for your soul, it searches for El Sol. Soul searcher, which gives you an approximate indication, but the soul searcher is never perfectly aligned with the telescope. And so you have to move the telescope around a little bit until, somebody else is sitting on the computer looking at the image that is transmitted from the camera. And as one of the students moves the telescope around, another student says, "Oh, there it went." do the reverse of what you just did. So it takes a little while to get this, but eventually you find it. Just takes patience. This is a good tool for teaching teenagers patience. It's also a good tool for teaching us patience. So you do that. You find the sun. And then you have to make sure that you are in proper alignment. So you push the buttons and the thing moves, and it's supposed to move horizontally in the computer field, but it moves diagonally, and so you realize that the camera is not oriented properly, and so you orient the camera properly so that it moves just exactly as it's supposed to. And once you've got that all set, then you zoom in on something, a sunspot, hopefully. We haven't had very many lately. Or the edge of the disk or something, and then you look for a tendency to drift, and if it drifts in a certain way, then that means your polar alignment isn't quite right, and so you adjust that. More fiddling, and eventually you're ready to start taking calibration. And so the calibration data means first you have to undo what you did at first and move the telescope off the sun. Position it on some blank piece of sky, and take a whole 2 minutes of calibration frames, blah, 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 blah. Then you put that's with the solar filter off. You're just looking at blank blue sky, hopefully. No clouds, hopefully, right. Then you take the solar filter, filter's already. Then you put the dust cover on the telescope, and you take another 2 minutes of frames. This is to measure what the CCD camera is responding to when there's no signal coming in, because that can mess up your data eventually. So you do all of that. And then once that's all done, then you have to come back and acquire the sun again. So you have to go through this rigmarole, moving the thing around, finding, there it is, nope. Eventually you get it. You have to do that twice then, every time. Then you sit and you wait for totality, or in the cases of our practice things, we say, okay, now's the time. You go, you push a button, and the camera does these, 8 sequences of 8 exposures until you're finished. At the end of all that, what you want to do is take a quick look at the exposures that you've taken. Because you've taken some with very short exposures, some with very long exposures, and you want to combine them somehow. And so there is this technique called high dynamic range imaging, where many of your cameras, in fact, a lot of the cell phone cameras have HDR features, where very quickly the camera takes 2 pictures at different exposures and then combines them in some optimal way. And in your cell phone, or that's done by some algorithm that's cooked up in Bellingham or Cupertino or wherever. In a DSLR like a Canon, there are you can take these you can do this automatic exposure bracketing, it's called, in most DSLRs, and you can take a sequence of 3 exposures or whatever, and then either you can let the Canon software combine them, or you can download them as raw images and combine them yourselves using an HDR program. So we have a MATLAB program that controls the Arduino and also does the software, some initial software processing for us. And so what it does is it takes these 8 different exposures and combines them into a single HDR image. This has been tried the same group of people had done this in an eclipse that occurred over Indonesia last year. And this is one example of what they've done. It's not a particularly good example, but the idea is that you can see at this, in the same image, some of the very bright features right at the edge of the sun, as well as some of the tendrils and so forth, the fainter features that go on out. And the idea is that using the assembly of HDR images from each one of the 68 sites across the country, that we can get this 90-minute dynamical movie of what's happening in the inner corona of the sun. There will be 2 attempts to do that. One will be done on the day of the eclipse with just this rough cut HDR stuff that we do immediately after taking the images, and then another will take months of study by folks in Tucson of looking at all of the detailed images themselves and then splicing them together in some way.
So Galen, how long does totality last right there in one spot? Does it last that 2.5 minutes?
So where we will be, it lasts about 2 minutes and 20 seconds. It depends on where you are with respect to the center line and where along the center line you are. The longest spot for this particular eclipse is somewhere in Kentucky, I think it is, at 2 minutes and 35 seconds. If you're right on the edge of totality, you only get it for a second. So I know somebody who's going to go up to a place in Oregon where you'll see it for 9 seconds. What's that? We won't get totality at all here. Here we will get 80% obscuration of the sun, which means that the sun's brightness will dim considerably, and we will see a crescent if you look at with the solar glasses that have been passed out. Or the other thing you can do is hold your hand up and look at the little pinholes between your fingers. You have these little pinhole cards too. Leaves on trees make excellent pinholes, and you'll see lots of little crescents on the ground, on pavement, from that. But you won't see the corona. You can't see the corona unless you're at 100% totality. So any place that's outside of that 70-mile band will not see the corona. So that's why the people are making plans to get into the path of totality, and I've seen all kinds of horror stories about what the traffic's going to be like in South Carolina and in Oregon and Idaho. We're hoping it's not going to be terribly bad in Idaho, but we don't know for sure. We won't know until we get there. I'm planning to go 2 weeks in advance to make sure that I get the site and that I have enough room for all my 8 kids and their chaperones and the teachers and a couple of people from Peak who will be accompanying. So that the place that we're going to be at is a Bureau of Reclamation site. It's first come, first serve, but you have a 14-day camping limit. So if I get there 2 weeks in advance, I think I can hold on to it for that long. That's my story. Yes?
So during the 2 minutes and 20 seconds the sun's going to meet, and through experience I know that keeping your camera on the sun is a big challenge without some kind of
Right. So the telescopes the telescopes and mounts that we have are equipped with drives. And they're sidereal clock drives, which is slightly different from the sun's rate across the sky, 4 minutes per day basically. But it's good enough in the 2.5 minutes of totality that we don't have to worry about it. I mean, we can tweak it a little bit while the camera is taking pictures, and it won't hurt that much, So we can do that. But yeah, it's important to keep tracking the sun during those 2.5 minutes because otherwise you'll lose it. Yes.
Chris, I'm curious how the video in all the high definition images are going to help you identify what the mechanism is that transfers the energy to the corona.
Right. I mean, we won't get the answer itself from those images. I mean, we'll get some clues, And then, I mean, it will also help because we have SOHO looking at the active magnetic field on the sun, and from the outer corona, it's impossible to trace where those tendrils come from. But from the inner corona, it's much more likely that you can trace where they come from, and can pin them down to specific active regions or regions on the sun that are responsible for it. And so SOHO will at the same time be imaging dynamically the surface of the sun, and so we can hopefully the hope is that we can by that means identify specific regions that are connecting to the inner corona, and then you have to invent a theory that how it's actually connected. But it's better than what we have now. So yeah. So I won't guarantee that this time next year we'll know the answer to that question, but I think we'll know more than we do now.
Is anybody going to fly an airplane that can go 1,000 miles an hour?
1,000 miles an hour. Well, I mean, people have flown through eclipses before, and I'm sure people will do that. I mean, maybe Rick, you know about plans of this, or?
I don't know about plans.
Yeah.
Actually, we're going to have a talk next in a couple of weeks, and Pete, and one of the guys who did that was Chick Keller, and Art Cox also did that with him. And they flew flights in the 70s. There was also one flight on the Concorde when it existed that was close to 1,000 miles an hour. And these guys were only about 550 miles an hour. And so they had a very long eclipse, but not, forever. The Concorde could actually, it kept up with the shadow moving across the Earth until it ran out of fuel. So they were able to keep up. Whether there's one scheduled for this eclipse or not, I don't know.
Yeah. Of course, it would be good to be able to keep up with that shadow. The problem with doing anything on an airplane is stability. It's hard enough keeping up with the sun when you're sitting on solid ground, as tracking and so forth. To do it on an airplane, these guys did it, right? So there must be solutions to that, but it's pretty tricky. Yes.
So on your video, is that just visible light spectrum, or are you?
This is white light.
Okay, so you're not going into UV where you might see
right.
really high temperature.
No, no. This is just white light. This experiment, which is called CATE, Continental-American Telescopic Eclipse experiment, is it's an experiment. Both to study the inner solar corona, but also an experiment in doing citizen science with relatively sophisticated equipment that can be bought relatively cheaply, right? So we have some corporate sponsors that provided the telescopes and the mounts to all sites. There's money from NASA that bought cameras and Arduinos for most sites. Not my site. I had to buy my own $1,400 camera and so forth. This was done. To do something in infrared or ultraviolet or something like that would have upped the cost considerably. It's not to say that can't be done in 2024, for example, which is another eclipse that doesn't cover quite as much territory of the United States, but it covers a fair swath of the southeastern United States. It's going to be cloudy there, but we'll try. I'm sure people will try. Yes.
I had to do that calculation. I couldn't stand it. So
did I get it right?
The distance from here to the moon is 240,000 miles, more or less.
Right.
92 million miles to the sun. So that's 0.0026 ratio. So if that fuzzball there were 4 inches in diameter, the moon would be 0.01 inches in diameter, thousandths of an inch.
Right, and your arm.
Fuzzball were the other wall.
Right, your arm isn't long enough.
1 inch away from your eyeball.
Right, your arm isn't long enough to do the experiment. Right. Right. Okay. Yes.
So what we were looking at, those great pictures of the corona. Now, what you're seeing in those pictures, it's not just what's occurring in that plane, right? Because assuming these tendrils are coming out all around the sphere of the sun. And so you're seeing some, yes, right at 90 degrees, but others are less. So is there a way to discern that?
I mean, that's the bugaboo of astronomy, right? I mean, we look at the sky and we imagine the sky as a two-dimensional plane, but of course it's not. You know, it's full of three-dimensional things, and so always you have to disentangle the third dimension. You know, how you do that differs from field to field and subfield in astronomy. You kind of do it the same way that geologists look at things in the field. You know, what's more recent is what overlays, and stuff. And so, if you see things that overlay, you can say, well, they're closer to us, and stuff like that. But it's hard. That's only qualitative. That's it's very hard to get, a real three-dimensional picture from a real three-dimensional visualization or whatever from a two-dimensional picture. There are tricks that people do. I'm not really familiar with what is normally done in coronal studies, but yeah, we'll see. Yeah. Yes?
I was just curious, with the path going across the whole U.S., are there some colleges and universities with observatories that are all set up that will be running
yes.
in the path that you know of?
Right. Yeah, there are. The Carbondale, are you from? Okay, all right. Yeah. I mean, they have an observatory, right? Yeah, and so they're right in the middle, and they're very close to the longest duration point, and that's the one that I hear about the most. But I'm sure there are others, also community colleges and so forth. And there's one at Riverton, a community college, which has a small, they have some small telescopes there. Yeah, I mean, it's lucky when you have these things pass right across observatories, and the University of Illinois at Carbondale is certainly, keyed up to take advantage of their position there. There's also one in Paducah, Kentucky. Anybody from there? In fact,
Middle Tennessee State University in Murfreesboro.
Oh, right. Yes, Murfreesboro. Right, exactly. Right.
So
Yeah,
have a big show with
yeah.
planetarium.
Yeah.
I don't know if they're running any research observations.
Yeah. In fact, the only total eclipse that I've ever seen was at an observatory. It was March 7th, 1970, on Nantucket Island, of all places, at the Maria Mitchell Observatory. And I was an undergraduate at Yale at the time, and we made a field trip out to Nantucket Island. We're hosted by Dorrit Hoffleit, who's one of the premier. She was director at Maria Mitchell Observatory at the time, as well as being a professor of astronomy at Yale, and she's you know the name, right? A Bright Star Catalog. Yeah, very prominent astronomer who died just a couple of years ago. Yeah, I remember her being an old lady when I knew her as an undergraduate, and then I met her again some 30 or 40 years later, and she didn't seem any older. But sadly, she passed away just a couple of years ago. Yes?
I was at the eclipse, I forget exactly when it was, late 80s, 1990, something like that, in La Paz, Baja California. And
1991.
Perfectly clear. It was probably the best place on earth. And it was really interesting because it was a 360-degree sunset.
Yes.
The birds went to sleep, the cockroaches came out, I've got a whole carousel of slides if you're interested.
All right. So are you going to contribute to Rick's photography show?
Of course, you want
If
to.
you want to talk to me afterwards, maybe we can.
Okay, yeah.
Yeah. Rick's doing a.
35mm slides.
Yeah. Well, we can. Yeah, I'm sure you can handle that. Yeah. Yeah. I mean, there's lots of phenomena associated with the eclipse, and these high school students that we're taking up are interested in various aspects. There's one guy who wants to do shadow band photography. What happens in some eclipses is that you get these strange little snaky bands of ephemeral shadows that pass by in the last few minutes before totality and the first few minutes after. And there's lots of discussion about what actually causes them. It's probably, you know, the knife edge of the moon and differential temperatures in the atmosphere and refraction. I mean, you can wave those words around and maybe that's what it is, but I don't know exactly what causes it. And then there's the animal stuff, you know, the animal behaviors, and there's temperature differences. We will bring along an infrared thermometer to measure the temperature of the surface of the ground, and we will also have air thermometers measuring the temperature of the air. You know, so we can do some weather observations as well as astronomy. Yes.
I was just curious what the effect of the sunspot cycle is in the sun's rotation on the
Oh,
corona.
right. Yeah.
Either
In fact,
one of those.
In fact, I wanted to bring that up. So one of the most striking effects of the sunspot cycle